All right, so Joe, your slide is up. Yes, it is. So I want to introduce today's speaker, Joe O'Rourke, who is brand new faculty in CC. He just started with us this year, technically, but he's been in CC for a couple of years because he was until very recently a CC Exploration postdoctoral fellow. Before that, he was a postdoc at Caltech. Before that, he was a grad student at Caltech. And a master's student, a PhD and master's, and he got his bachelor's degree at Yale in 2012, which seems like just yesterday to some of us. So he's going to talk to us. Joe does a number of different things tying together the Earth's interior, planetary interiors, and planetary surface evolution. And he is going to talk to us today about mysteries from Venus, from crust to core. So Joe, the floor is yours.
All right, thank you so much for that introduction, and it's great to see so many people, at least on the participants list. I'm excited for the start of a new semester, get to see colleagues in new and old, and I hope to someday see many of you in person. So like Ariel said, I've worked on a tremendous number of destinations in our solar system and beyond, but today I'm giving a talk just about my favorite planet, which is Venus, Earth's evil twin and the missing link to many theories of our solar system's formation and evolution. So overall, my research goal is centered on understanding how the dynamics of planetary interiors influence surface properties. So a lot of phenomena that control the habitability of surfaces over time, like volcanism, tectonics, magnetic fields, atmospheric outgassing, they all arise from things that go on deep below our feet on Earth. So mantle dynamics and core crystallization. So my overarching goal is to build sort of general theories for how planetary interiors work and apply that to everything from terrestrial planets to large asteroids to icy satellites, even to exoplanets. But like I said, today I'm just going to talk about our nearest celestial neighbor, which is the planet Venus. And Venus is more than enough to include in one talk, because any study of Venus, and especially its deep interior, has to be massively interdisciplinary by necessity. So today you'll hear a talk about the high-level science questions that I think are most compelling for Venus. And to answer some of these questions, we have to blend observations from spacecraft, we have to do fundamental geology, and we have to try to interpret spacecraft observations with a combination of numerical modeling and theory. And so just to situate everyone, get everyone on the same page, Earth is the third rock from the sun, and Venus is just one closer in terms of the major planets. So if you were an alien astronomer looking back at our solar system with the sort of technology that we have to observe exoplanets today, you would think that this planet Venus is extremely similar to this other planet, Earth. So Venus is an Earth-like planet in terms of all the things we can measure for exoplanets today. It's about 80% of Earth's mass, it's 95% of Earth's radius, and so its surface gravity is basically the same as Earth's, and its bulk density is the same. And so again, just I can't emphasize enough that if we were observing an exoplanet today, if you want to call it an Earth-like exoplanet, you might as well call it a Venus-like exoplanet. And people have speculated about what Venus is like for a long time. It's the second brightest object in the night sky, so it's pretty hard to miss. But unfortunately, if you look at it in visible wavelengths, what our eyes can actually see, Venus is basically featureless. It's an extremely bright, almost uniform sphere. And it turns out that Venus is so bright that even though it's a bit closer to the sun, it reflects more sunlight. And if you calculate its black body temperature, you find that Venus would be colder than Earth if it were just an atmosphereless ball that is painted with paint with its current brightness. So people for a long time thought that maybe the reason Venus is so bright is that it's covered in clouds, just like Earth is. We have nice fluffy water clouds, but unlike Earth, maybe Venus has a continuous blanket of clouds. And so maybe Venus is just this swampy, water-rich, but otherwise Earth-like world. So I always love to quote Nobel Prize winners making fools of themselves. And one of my favorite quotes is from Arrhenius, the famous physical chemist. And he confidently proclaimed a little over 100 years ago that Venus is no doubt covered with swamps. And indeed, if you look at old sci-fi, like pre-1950s sci-fi, you find tons of stories about people hacking through the jungle and riding dinosaurs on Venus. Unfortunately, that's not the case. Since the 1950s, we suspected that the surface of Venus was actually hell based on the amount of millimeter wave radiation that was coming off of it. And the first ever interplanetary spacecraft mission confirmed that our nearest neighbor is Earth-like in many respects, but not an Earth twin in the important respects. So Mariner 2 was the first successful interplanetary flyby. It flew by Venus in 1962, and it conducted microwave sounding to measure the surface temperature of Venus and found that it was hot, hot, hot. The surface temperature is 740 K, which is famously hot enough to melt lead. And the reason that it's so hot is that the atmosphere is not just very cloudy, but it's actually 90 times as massive as Earth's. And the atmosphere is almost entirely carbon dioxide. So there is a supercharged greenhouse effect that skyrockets the surface temperatures at present day. Now, eventually we sent spacecraft that could look below the clouds, and we got our first ever glimpses of what Venus looks like on the surface. These are some images from the Soviet Venera landers that landed in the 70s and 80s, I believe. And you can see that the landing sites don't look exactly like anything on Earth, but they sort of look like lava flows. And in fact, the Venera landers conducted some chemical analyses and found that the rocks near the landing site were roughly basaltic. And so it's commonly believed that Venus is mostly covered by basaltic lava flows, which is what we would find at the bottom of the ocean on Earth. So it wasn't until the 1990s that we got a decent map of the entire surface. So like I said, you can't see through the atmosphere and the visible. And so NASA sent a radar orbiter to Venus called Magellan. And Magellan began its science operations when I was 10 days old, and it assembled the first global map of Venus. And this is what it looks like on the surface. And it looks very weird. It looks totally unlike Earth. So Earth has oceans with spreading centers and continents. Venus maybe has some continent analogs, but it definitely doesn't have a system of plate tectonics like Earth. And Venus is known to have active volcanism. There's volcanic gases that would be short-lived in the atmosphere, implying that they were recently belched out by a volcano. And also there's some signs that there are fresh lava flows on the surface. So Venus has active volcanism, but the volcanism and the tectonics aren't organized into what we would recognize as a plate tectonic regime. So Venus is an enigma, I would say. And it's problematic that the planet that is most like Earth in the basic respects is so unlike Earth in the respects that we actually care about scientifically. And so I would say that until we understand why Earth and Venus are different, we have no basis for claiming that we can understand anything about the general evolution of terrestrial planets. And if we think we're going to characterize exoplanets that are rocky and Earth-sized, we need to understand Venus, which is the exoplanet in our backyard. So as many of you probably know, the planetary science community is gearing up for an exercise called the Decadal Survey, where NASA, or where we will prioritize for NASA the most important missions to pursue in the next decade. And the community, the Venus community, recently came together to say what its top line goals were for Venus exploration. And a fun fact is that I got to be co-chair of this committee after a few months of contentious meetings where the current chair was sort of sick of everyone and no one else wanted to do it. So a bloodless coup on my behalf. But the top three priorities for Venus exploration are to understand whether Venus was ever habitable in the past, to understand the atmospheric dynamics and composition today, and to understand the geologic history that's preserved on the surface. And so I'm going to talk about science goals and science questions that are related to the first and the third of these broad-based consensus goals for Venus exploration. And specifically, as promised by my title, I'm going to start at the top of Venus and work our way down. We're going to talk about the crust, the lithosphere, the mantle, and then the core. And as we go down into Venus, we're also going down into time because the crust preserves the geologic history over the last billion years, but mantle dynamics are a reflection of the evolution of Venus over billions of years. And I would argue that the properties of the core are a signal as to how Venus was put together in the very beginning. So we're going into the deep interior, and the deep interior is deep time. And I really want to start out by telling a provocative story that will motivate asking the questions that I'll ask. So the provocative story is that Venus and Earth began as twins. They both had oceans for billions of years. Maybe they both had life. But then something very bad happened to Venus. And within a few 100 million years, Venus went from a clement paradise to the hellish wasteland that it is today. And so just to be a little more sciencey about that story, the idea is that when Earth and Venus, they formed from the protoplanetary disk, they went through a phase where they both had magma oceans, and the outgassing of a magma ocean set the properties of the atmosphere. And so one theory is that Venus and Earth went through the magma ocean phase in a similar fashion, so that when they originally formed 4.5 billion years ago, they had thin atmospheres with clement surface temperatures. And then even though Venus is closer to the sun, this old view, if it had more clouds, the clouds can actually keep the temperature of Venus cold for a long time. But over billions of years, the solar flux increases and Venus eventually enters a runaway greenhouse effect. And that alone could explain the high surface temperatures on Venus today. The problem with this model is that you also have to explain how 90 bars of CO2 got into the atmosphere. So this atmospheric evolution model is also a geologic model, because it posits that the catastrophe that occurred 1 billion years ago was not just an atmospheric calamity, but it was also a geologic calamity. And you have to posit a planet-wide, all-encompassing episode of volcanism that resurfaces the entire crust and releases huge amounts of volcanic gases into the atmosphere all at once to go from a clement Venus to a hellish wasteland Venus that we observe today. So my question for you, and hopefully the poll that we set up before everyone logged on will work, is maybe many of you have heard this hypothesis before, but how many of you believe it, just sort of a priori based on what I've said in the last 10 minutes? Could we possibly get the poll up and see? So I'm asking you to guess if you think that this story I told that Venus was an ocean world, if you believe it, and also tell me if you're confident in that guess.
So the poll's up. I don't know, is it live view? Can you guys
Yes,
see the answers live as they come in?
Responses are pouring in. The audience is so engaged. They love the energy. All right, I'm going to give it another 5 or 6 seconds. Okay, great. So I will end the poll. And so the results are that it's about half and half. You're split. A lot of you find this hypothesis compelling. Maybe you believe it, maybe you don't. And only a brave quarter of you are courageous in your guess. So I would say that I followed the conventional wisdom exactly, which is that I'm not sure if this story is true, and I'm definitely not confident about any claims I'll make. So let's delve into this a little bit more, into way more detail. I think we can all agree that if Venus was an ocean world for billions of years, that's like super awesome to know, and we should try to find out if we can. So let's see if what would it take to get definitive answers. Oh, so I should point out that even if Venus wasn't a habitable world, it's still a very active world. So we know that Venus has had volcanic activity now. It almost certainly had it in the past. It could have had a magnetic field until very recently, and as discussed, it could have had sea level water. So just to compare to another planet, which I like a lot, but my purpose in this talk is to shill mindlessly for Venus. Mars is sort of geologically dead now. If it had surface liquid water, it only had it for about 1 billion years. And we know that it didn't have a magnetic field for very long. So if you're interested just in general active terrestrial planets in our solar system, you can't go wrong with Venus as a laboratory for understanding planetary processes. Okay, so I specifically want to tackle 3 questions that this habitable hypothesis that I showed makes predictions about. So the first for the crust is, what is the age of the surface? Like I said, the prediction is that there's the surface is about 1 billion years ago, billion years old, because that's when this catastrophe occurred. For the mantle, the prediction is that the mantle is relatively quiescent now. That after this burst of activity, volcanism is slowed down, but the crust should be very thick, and the mantle should be cooling much slower than Earth's mantle is cooling today. Obviously, there's no dynamo now, and this catastrophic habitability scenario would say that we can't ever know if there was a magnetic field in the past, because this massive episode of global resurfacing would have erased any remnant magnetization that may have existed. And so we're going to tackle each of these 3 questions in turn. Uh, and for each of these three questions, we're going to have to use a different approach. So this is why I promised that me giving you a talk about one planet would actually be a tour of methodologies. We're going to go from geology to space physics in the next half hour or so. So fasten your seatbelts. Okay, so if we want to understand the age of the surface, we have to employ one of the oldest, most traditional techniques in planetary science, which is crater counting. So the fundamentals of this are extremely simple. Over time, planets get hit by stuff. And so if you have a surface, as it gets older, it will gradually acquire more and more impact craters. And if there's a resurfacing event, that'll wipe it clean. And so the number of craters, if you think you know the cratering rate, the number of craters gives you an estimate for the age of that surface. So how long it has been since it was last covered by volcanism at a depth sufficient to bury all the old craters. So on the moon and the Mars, they all have surfaces that are in parts like 4 billion years old or close to that. And so they have millions of impact craters ranging from craters that are almost hemispheric in size down to very, very small. But Venus is a great planet for lazy crater counters because there's only about 1,000 impact craters. Remember, there's an extremely thick atmosphere. So if there are impactors that are below a certain size, they just blow up in the atmosphere, like the Tunguska impact on Earth that shattered all those trees in Siberia. So there aren't any impact craters on Venus that are smaller in diameter than about 5 kilometers. And because the surface of Venus is young, there aren't that many big impact craters because all the big asteroids and stuff that would hit the planets mostly hit the planets at early times in our solar system's history. So we think we know about basically all the impact craters that currently exist on the surface of Venus today. And so it just so happens that the cratering rate you expect from studies of the impactor population is about 1 crater per million years. There's 1,000 craters on Venus. So the quote unquote cratering age for Venus is about 1 billion years. And so the real question is whether that cratering age is the actual age of the entire surface. And this map that I have on the left is an equal area projection of the surface of Venus. And I've plotted the location of all the different impact craters. Don't worry about the different colors or the different symbol shapes. So what you might notice if you have a tuned eye for this sort of stuff is that the latitudes and longitudes of impact craters, they look pretty random. And indeed, if I just drew a population of 1,000 random coordinates and plot them down on a map of Venus, I would get cratering statistics that were equivalent to the statistics of the actual impact craters on Venus. And since we think that impacts are spatially random, one easy explanation of this apparent randomness is that the surface was wiped clean all at once and craters have just been building up since then. Now, what this would predict is that all these craters on Venus should be pristine if there hasn't been much volcanism since the great resurfacing. And there, it turns out there's a huge controversy about how many craters on the surface of Venus are pristine. So on the left, we have a crater that everyone agrees is pristine. And this is imaged with synthetic aperture radar, so it looks different than a visible image. You can think that bright areas on this radar image are rough areas, and the dark areas are smoother, just as a heuristic. So you can see on the left that this 70-kilometer diameter crater is, you can see the rim very clearly, you can see the ejecta blanket very clearly, the ejecta blanket looks complete, and you can also see, it doesn't have a central peak, but you can see rough terrain in the center of the crater. And this is about 20% of craters on Venus that are obviously pristine. And then we have a few craters on Venus that are obviously modified by volcanoes. So you can see here that this massive flow came in from the top and just buried the crater, buried all the ejecta, and you only have a bit of the rim sticking out. But the real controversy about Venus is that there are 80% of craters that are sort of in between. So about 80% of all craters, they have radar dark floors. So you could interpret this as a crater where there's been a volcanic flow that has either erupted from the floor or has breached the rim at length scales that you can't see on the radar images, which have a pixel scale of about 125 meters, and they could be partially filled. Oh, sorry. And so it's unknown if these radar dark floors indicate volcanic modification. I've done some detailed statistical analyses of the spatial distribution of these dark floored craters on Venus. And if these dark floored craters are modified by volcanism, then catastrophic resurfacing did not happen. The cratering age would underestimate the average age of the surface by about a factor of 2. So we've addressed our first question, but I have to answer it with the shrug emoji right now, because we don't know if the prediction has been falsified, but we have a sort of more refined question that we can ask, which is at least a step forward. So let's move on to the next question. Maybe we'll have better luck, which is how fast is the mantle cooling? And remember that the prediction of the particular provocative story that I told you is that it's cooling way slower than Earth is now. And the approach that we're going to take is totally different. We're no longer going to worry about impact craters, but we're going to employ other techniques to study the lithosphere of Venus. So the first question is, what is the lithosphere? So I've been showing this cartoon of Venus's internal structure, and I've had things colored based on their composition. So the yellow is the atmosphere. This sort of grayish green is the crust, and the green is the mantle. And so the mantle is the silicate rocks that make up the bulk of the planet of Venus and also Earth. And the crust is the rocky layer that is derived from partially melting the mantle. So if you heat up the mantle a little bit, you get volcanoes. And when the volcanic rock cools, you get crust. So this is a compositional definition for the layering within Earth or Venus. We can also define some layering based on rheological properties. And that is what's useful to estimating the heat flow. So if you took intro geophysics, you would have learned about the lithosphere, which is the part of the planet that is relatively cold, and so it is relatively rigid. It doesn't flow like a fluid, it deforms like an elastic plate. And so this lithosphere includes the crust and also the upper portion of the mantle. And down in the mantle, it eventually gets hot enough that the rocks become gooey, they become ductile, to use the technical term, and they can flow like a fluid. And so the reason it's useful to contemplate the lithosphere is because we sort of know by definition what the temperature profile is inside the lithosphere. Because if we make assumptions about what the lithosphere is made out of, we know the temperature at which it starts to flow. And so that temperature for dry olivine, it's a little over 1,000 degrees. The surface temperature is 740 degrees. And so we can posit that there's a temperature gradient within the lithosphere. Now, heat flow is just the slope, basically, of this temperature gradient. It's the temperature gradient multiplied by the thermal conductivity. So we know the temperature change across the lithosphere, and we don't know the thickness of the lithosphere, but if we did, we could use that to quickly calculate the heat flow and compare that to the heat flow from Earth. So you might wonder, why don't we just go directly and measure it exactly? And this is what the InSight lander is trying to do on Mars right now, but it's really hard. So one way you could measure this just directly, which would be sort of the gold standard measurement, would be to sink a probe into the surface and measure how the temperature varies with depth. This is what InSight's trying to do, but they're having a hard time getting the mole to actually penetrate the weird rocks that they found at the very top of the surface. So hashtag save the mole, but it's way harder to do on Venus than Mars. So we might be waiting a while for this sort of experiment. The other way we could directly infer the thickness of the lithosphere is with seismology. And right now there's no seismometer that could survive on the surface of Venus for as long as you would need to actually measure some Venus quakes. But just a couple months ago, actually an ASU group led by Lenore Dye, who's the head of SEMTI, including a bunch of CC COIs, including me, were awarded nearly $1 million from NASA to build a prototype seismometer. So we can't do seismology on Venus yet, but stay tuned. Maybe stay tuned for the next decade or so, and we can get it done. But what we can do right now, without waiting for a far future spacecraft, is to indirectly infer the thickness of the lithosphere by looking at how the lithosphere bends in response to loads. So this is an extremely classic thing to do on Earth. If you have this standard geodynamics textbook, it's just chapter 3, I believe. And the point is that if you have a large volcano sitting on the top of the lithosphere will bend in response to that load. And it will bend with a wavelength that is a one-to-one function of a lithospheric thickness. So if you can look at the topography around volcanic features, in principle, you can infer how thick the lithosphere is there. So this has been done, it can be done pretty well for the Hawaiian Islands on Earth, which are just big seamount volcanoes. So the challenge is to find sort of analogous features on Venus. Something I've looked at a lot are these enigmatic volcanotectonic features that are called coronae. Corona, as we all know now, means crown. So these geologic features are defined by this annulus of concentric fractures. They have a bunch of different sizes on Venus. So these are sort of some mid-sized coronae, but they range from about 60 kilometers in size all the way up to 2,000 kilometers. The largest feature on Venus is Artemis Coronae, which is one of these oddballs. And they probably form from mantle plumes interacting with the lithosphere, and they might be sites of incipient subduction on Venus. So they are extremely interesting volcanic and tectonic features. I am going to somewhat obscure their majesty by just treating them as like big heavy loads on the lithosphere that we can study to try to find this one thing I've said I care about for now. A couple of years ago, Sue Smrikar at JPL and I did a sort of pilot study where we looked at a new topography data set that became available for Venus based on the processing of some old images. And we found flexural signatures at 19 coronae out of about 100 that we looked at, which is about 20% of the total population. And we found that they were associated with very thin elastic lithospheres. So about 10-kilometer thick lithosphere, which corresponds to a heat flow that is over 100 milliwatts per meter squared, which is higher than the average value for Earth. This would indicate that if you thought that the heat flow from coronae were globally representative, that Venus would be cooling down much, much faster than Earth is, which would be surprising. I should say that our pilot study, because it worked, another student has taken on doing a global survey, and they found about 80% more signatures, or a few times more signatures, and found similar results. So the big question here is whether or not these coronae, these elastic thickness inferences, are representative of Venus globally. So technically, it could be the sort of regional average, or it could just be the peak heat flow that happened during the formation of the coronae that we're inferring here. So like I said, the coronae, they form from the interaction with a mantle plume and the lithosphere. Mantle plumes are quite hot, so it might be no surprise that they produce localized heating. So CC graduate student Madison Borelli, who's been working with me for all of 6 or 7 months, had the great idea to try to conduct this analysis at a different type of geologic feature on Venus, which are called steep-sided domes. They're exactly what they sound like. They're these mid-sized volcanoes that are about 20 or 30 kilometers in diameter. And she found flexural signatures at about 15 or 20% of the steep-sided domes that exist on the surface. She looked at every single one of these that we know about on the surface of Venus, and found that elastic thicknesses there were about twice, or in many cases, 3 times as thick. So the steep-sided domes seem to form or be associated with regions of the lithosphere that are cooling slower than Earth. So except for the domes that are right next to coronae, and those with thinner lithosphere and higher heat flow. So this is a really vital result, because it breaks a degeneracy in the interpretation of the results from coronae. And it really reveals that volcanomorphology on Venus is a probe of the elastic lithosphere. And it suggests that Venus overall might be cooling a little slower than Earth. Now, how did I get to that broad conclusion? Well, the punchline is that these local estimates of lithospheric flexure, they agree with results that were derived from a global survey of elastic thickness that used gravity data. Now, the gravity data have been treated as pretty sketchy for a long time because they have very poor spatial resolution. So fundamentally, anytime you're doing a gravity survey with spacecraft, what you're doing is you're tracking the acceleration of a spacecraft, and your spatial resolution is no better than the altitude at which the spacecraft goes. And since Venus has a thick atmosphere, you can't get any closer than about 200 kilometers. So that's the best resolution of the gravity field. But this tentative gravity result from 2006 was suggestive, because it indicated that about half of Venus was cooling faster than Earth, and about half of Venus was cooling slower than Earth is today. And when you sum everything up, you get that Venus would be cooling just a little bit slower than Earth is today. Great. So this is the first really result that I have that I'm willing to put more than a big shrug emoji for. Still is a little shrug emoji, because we're pushing the resolution of the gravity and the topography data sets. But I would say that that Venus is cooling just about as fast as Earth is now. which explains why it's so volcanically active. And so this is the first prediction that sort of diverges a little bit from the provocative habitability story that I told you earlier. But you might say, oh, sorry, I have this other question about whether the mantle is solidified. And if you're an expert on planetary interiors, you've probably thought that this cartoon I've been showing you for Venus is very strange because it includes a layer that's not present in most internal structure cartoons. So I should maybe explain this cartoon that I've been throwing up for the last half hour. And this is saying that Venus has a basal magma ocean. So on Earth right now, we know that except for maybe a kilometer or two at the very base of the mantle, the silicate mantle of Earth is completely solid. But I'm positing that the basal mantle of Venus could be molten, and that there could be a molten layer that is up to 400 kilometers thick. And this, if we detected this, that would be the signal that Venus over time has been cooling slower than Earth. Let me walk you through why I believe that is true. So there's when planets form, especially bigger terrestrial planets like Earth and Venus, they start out pretty hot. And there's actually enough heat in the formation of an Earth-sized or a Venus-sized planet to melt the entire mantle. It's not clear that Earth's entire mantle was molten when it formed, but it's quite plausible. And it turns out that if you look at the melting curve of Earth's mantle, it changes dramatically based on pressure. So if you increase the pressure, the melting temperature of rock goes up dramatically. You can compare that to the temperature that you expect in the molten mantle. And it turns out that the melting temperature, or the actual temperature, might cross the melting curve at mid-mantle depths, so that the mantle, instead of solidifying from the bottom up, actually solidifies from the middle outwards. And in a very famous Nature paper back in 2007, Stéphane Labrosse published this model arguing that Earth had a basal magma ocean. Sorry, I'm losing my slides. There we go. And so in his model, this superficial magma ocean solidifies within about 10 million years, but the cooling rate of this basal magma ocean is limited by the rate at which heat can be pulled out by solid state mantle convection. So transporting heat from the deep interior through the solid mantle is orders of magnitude slower than having heat just radiate directly to space, as you can expect. So the basal magma ocean takes a lot longer to solidify, and in these models, it solidifies only about 2 billion years ago. Well, guess what? The habitability story for Venus that I told you predicts that Venus is cooling about half as slowly as Earth. So when you run the detailed numerical model for the solidification of a basal magma ocean, you get that the internal structure of Venus today, it resembles the internal structure of Earth about 2 billion years ago. And therefore, this basal magma ocean that's solidified in Earth's Middle Ages, in the Middle Ages of Earth, not the Middle Ages of human society, 2 billion years ago would still exist today. And it would take another couple billion years for it to solidify. So from local geologic features on Venus probes the elastic thickness at present day on Venus. But it's the mantle structure that can really tell us what the cooling history of Venus has been integrated over billions of years. So I'll say that the cooling history, the cooling rate of Venus relative to Earth now is pretty similar. And what the cooling rate is over in the past is unknown, but it's testable with future missions. Okay, so now let's turn to the final question, which takes us down into the core, which is, was there ever a magnetic field in Venus? And right now we just have a shrug emoji. And I'm going to address this question with conjecture and speculation, but it's conjecture and speculation backed up by very sophisticated numerical simulations and theory. And I'll of course talk about the actual data we should gather to figure things out. Great. Again, the basic question is if we're going to ask why Venus doesn't have a magnetic field, we should maybe ask why Earth has a magnetic field. And so the fundamental reason that Earth has a magnetic field is that 2,000 miles below our feet, there is this ocean of conductive fluid that is vigorously churning. So we know that Earth has an outer core that is almost entirely iron. Iron is electrically conductive, and it has the viscosity of water, basically, even under these extreme temperatures and pressures. And so we think that this giant, bigger than the moon, ocean of liquid iron is very vigorously convecting. And because it's electrically conductive, if you move conductive fluid you get a dynamo effect. So a dynamo converts mechanical energy into electrical or electromagnetic energy, and that is what produces our magnetic field. And so the dynamo process within the core is extremely complicated, but if you get far enough away from the core, you only see the dipole components of the magnetic field. So it's sort of like Earth has a bar magnet just stuck in its inside, but Earth totally doesn't have a bar magnet in its inside. It has a complicated dynamo. So the reason that Venus doesn't have a magnetic field is because it does not have this convecting ocean of liquid iron that Earth has. Now, we think that Venus has the ocean of liquid iron, but it must be that this ocean of liquid iron is not convecting. And that could occur because Venus is cooling down just a little bit slower than Earth is, like I've been saying. It turns out if you run the models, the rate required to drive convection in the core is sort of close to the rate at which we think Earth is cooling down. So if Venus is cooling just a little slower than Earth, there's no convection, no magnetic field in the core. It's sort of like if you have a pot on a stove, obviously you need to turn the heat up enough that it should boil. So Earth is sort of just boiling, and Venus, someone turned the stove down a little bit on Venus. And so the Venus pot is not boiling. Okay, so I should say that what I just said on the last slide is like the standard story for the dynamo on Earth, which is that the reservoir of conductive fluid is the core. This basal magma ocean hypothesis for Earth is really intriguing because liquid silicates in the basal mantle, it turns out they're electrically conductive. So if you melt a rock, if you look at magma or lava on the surface of Earth today, and you measure its electrical conductivity, it's extremely low. You wouldn't have a dynamo because of lava on the surface of Earth. But when you squeeze liquid silicates to extreme pressures and you heat them up tremendously, their electrical conductivity increases by a few orders of magnitude. And so it's possible that Earth had a dynamo in its basal magma ocean a long time ago. And so at early times, if you have a basal magma ocean, you have these two potential hosts of a dynamo. And the basal magma ocean is a compelling hypothesis because it's otherwise hard to explain why Earth has such an old magnetic field. Should have said at the beginning, we know that Earth has a magnetic field now, obviously, and the magnetic field existed back in time as far as we have data. So you find an old rock, it'll show, if it can show whether or not there was a magnetic field, it'll show that Earth had a magnetic field. So we have no evidence that Earth ever did not have a magnetic field, if that makes sense. And the basal magma ocean hypothesis also solves some other geochemical conundrums that I can't really get into right now. But we should run similar models for Venus. But first I want to delve just a little bit more into what data we do have. So you'll commonly read that Venus has no dynamo, which I think is a pretty secure conclusion, but our constraints on the magnetism of Venus are actually quite limited. So the first constraint came from Mariner 2, this first ever interplanetary flyby. It flew super far by Venus, and all it was able to measure is that Venus didn't have a magnetic field that was stronger than Earth's. It didn't get close enough to the planet to make any more detailed conclusions. But the Venera 4 lander, well, the magnetometer on it didn't actually make it to the surface, but it faithfully collected data down to about 25 kilometers altitude over one particular location, and it didn't detect any magnetic field. So no internal magnetic field, and there was no crustal magnetic field, at least at that location, that could be detected. Now, in the next decade, we started sending orbiters to Venus that had magnetometers. Pioneer Venus orbiter was fairly magnetically clean, and it got down to just a little under 200 kilometers altitude from Venus at the equator. And it placed the strictest upper limit on the strength of any magnetic field at Venus. So it found that if there's a magnetic field at Venus, its global intensity has to be less than 1/100,000th times the strength of Earth's magnetic field. And there was one orbiter that went at a different orbit at Venus. So it reached its lowest altitude over the northern hemisphere, and it didn't find any crustal fields there. It was actually a little more magnetically dirty than Pioneer Venus orbiter was, so it didn't place any more stringent constraints on the global magnetization. So the takeaway you should have from this is that Venus has no internal dynamo, but crustal fields like we have on Earth and Mars and the Moon and Mercury and mini asteroids, those crustal fields would be a lot weaker than a dynamo. And super strong crustal fields could exist anywhere in the southern hemisphere, because we've never had a spacecraft reach low altitudes there. And sort of weaker crustal fields, comparable to like the sort of the bottom end of strengths that we see on Earth and Mars and the Moon and Mercury today, those could be undetected anywhere on the planet. So we have not done by any means a comprehensive search for magnetization on Venus. And I really argue that we should. So I've run a lot of numerical simulations that have mantle dynamics codes similar to what Professor Mingming Li does here at ASU. And one output of these codes is you can predict the heat flow from the core into the mantle when you're modeling the mantle dynamics. And the heat flow out of the core can be translated into a prediction for how strong the magnetic field is over time. And what these models predict, there's a lot of details that go into them, but they predict that Venus had an Earth-like field for billions of years. In fact, had an Earth-like field potentially until times that are within the cratering age of Venus, possibly within the surface age. And so this is for a sort of conventional model where the mantle of Venus is fully solid. If you add a basal magma ocean to the dynamo, what a basal magma ocean does is it actually insulates the core. So the core cools much more slowly. There's no core dynamo, but just like early Earth, you can have a dynamo in the basal magma ocean itself. And it coincidentally, I think it's a coincidence, predicts a dynamo with the same strength and about the same lifetime as the other models do for a core dynamo. So the conclusion of all these models is that if we assume that Venus is cooling slower than Earth today, then the dynamo history we predict is that Venus had a dynamo until recent times, until about the past billion years or so. And crucially, an assumption for this is that the initial conditions for the core and the basal magma ocean of Venus and Earth were the same. In particular, it asserts that Venus and Earth both started out super hot. If Venus formed in a different way than Earth, if it started out much colder than Earth, then it might not have had a basal magma ocean, and the core might have some thermochemical stratification that would preclude there ever being a dynamo. So if we found evidence that Venus had a magnetic field at earlier times, we would know that Venus and Earth, they formed in a similar way, but Venus has cooled more slowly since its formation. Okay, so how could we find out? I've invoked crustal fields a lot so far in this talk, and the reason that planetary crusts retain signatures of ancient magnetic fields is because some minerals in planetary crusts are magnetic. So if you have a volcano that erupts in the presence of a magnetic field, the magnetic domains in these minerals, like magnetite or hematite, they will line up with the ambient magnetic field. And if you cool the rocks down, the orientation of these magnetic domains gets frozen in. And even if you take away the field, this alignment of the magnetic domains decays very slowly. It takes billions of years for the domains to re-randomize. And so if you find an old rock, you can potentially infer the strength and the direction of the ancient magnetic field. That assumes you haven't heated it back up again. So every mineral has a magic temperature called the Curie temperature, where if you heat it up above that temperature, things re-randomize. So in order to record evidence of an ancient magnetic field, you need a crustal rock that formed in the presence of an ancient magnetic field, and it needs to have been cooled and remain cool below the Curie temperature for billions of years until now. So what are the possibilities of doing this on Venus? If you read a random sampling of papers in the literature, you'll find some assertions that Venus is too hot to record any magnetization over billions of years. So I had to write this paper about a year ago to point out that actually the surface of temperature of Venus, it's hot, but it's not too hot. Minerals like magnetite have Curie temperatures, or to be more technical, a blocking temperature, which is a bit lower than the Curie temperature, that are about 50 Kelvin below the surface, or 50 Kelvin above the surface temperature. So using representative thermal gradients in the crust of Venus, you can get about 5 kilometers down into Venus before you hit temperatures that are too hot for crustal magnetization. And so it's close, admittedly, it's close. If Venus was much hotter in the past, then it's possible that any remnant magnetization was just baked out of the crustal rocks. But a lot of models for Venus predict that how hot Venus is today is about as hot as it ever was in the past. And if that's the case, then there is definitely hope of producing, of retaining crustal magnetic fields if any were formed in the first place. And I think there's actually suggestive evidence that such crustal fields really exist. And this is some pretty speculative work that I'm working on in partnership with a space physicist at Princeton University, Shanfei Dong. So I mentioned that the upper limit for the magnetic field of Venus is about 100,000th the magnetic field of Earth. And if you convert that into units called a magnetic dipole moment, that upper limit is about 10 to the 17 amps per meter squared. Okay, well, 10 to the 17 amps per meter squared, those probably aren't units you're used to working with, but it's the units you get if you assume that about 5% of the crust of Venus is magnetized with a magnetization intensity of about 1 amp per meter. That's about the intensity we find on average for basalt on Earth or for crustal rocks on Mars. And if you assume that this 5% of the surface area is magnetized down to a depth of about 5 kilometers, you get a dipole moment of 10 to the 17 amps per meter squared. And Venus, because it has this thick atmosphere, it's in a really interesting space physics regime where any weak magnetic fields that are in the ionosphere, they get advected into the night side. So the way this cartoon works, on the left here, you have the sun and the solar wind is beating down on the ionosphere from the left. And any magnetic field that Venus could have, if it's a weak magnetic field, these field lines get advected down to the night side. And what's cool is that Pioneer Venus Orbiter, back in the 70s, 80s, and 90s, found some weird holes in the magnetosphere that could correspond to these field lines that have been advected into the night side. Now, this is just a cartoon model from the 80s, and no one has ever taken a look at this, a sort of a weak Venus magnetosphere using modern magnetohydrodynamic simulations, and that's what we're doing right now. And we think it's possible that we will reproduce these data, which to me would be a provocative sign that Venus does in fact have crustal fields, which would make sense since every other major planet in our solar system has crustal fields. Okay, so again, we asked 3 questions that bear directly on this habitable hypothesis for Venus, and we can't really confirm any of them right now. And I'm going to say that that's very disappointing. I wish we could. And the reason we can't is because Venus has been underserved in terms of spacecraft missions in the last couple decades by NASA. NASA has not sent a space mission to Venus since the Magellan mission, which is around the time that I was born. So we can't answer the basic questions, but we can ask better questions after doing a lot of work. And these better questions tell us what data we need to collect in order to solve these mysteries of Venus. So if we want to find out the age of the surface, we need to know if these impact craters with radar dark floors are volcanically modified. And that means we need high resolution images and topography with global coverage, so we can look at all 1,000 of these impact craters. If we want to know how fast the mantle is cooling, we need to figure out the current heat flow through the lithosphere. So we need high resolution images, topography, and gravity so that we can study lithospheric flexure. It turns out that gravity and tidal deformation will also tell you if a basal magma ocean exists deep within Venus. And we also need to know if there was any crustal magnetization. So an orbiter could do this by conducting a magnetometer survey in the night side magnetosphere. And we should also float balloons in the Venus atmosphere to search for crustal fields. Okay, unfortunately, there are missions planned to do just this. So you might know that both NASA and the European Space Agency are in the final round of selections for the next medium class missions in the sort of $500 million mark, like the NASA Psyche mission that Lindy is leading here at ASU. So there's a modern geophysical orbiter in contention for both of those competition, Veritas in the US and Envision in Europe. And both these orbiters would be amazing. They would conduct, oh, sorry. I've dropped all my slides. Oh no. Sorry. Okay, so the Veritas and the Envision missions, I'm desperately hoping that one of them will fly to collect these badly needed data sets. And the other mission, there's another mission that's a finalist for the Discovery program as well, which is called Da Vinci Plus. And it's a mission to measure the noble gases in Venus, which would constrain the atmosphere. They could help constrain if the thick atmosphere was primordial or if it was outgassed recently. And there's also implications for the spatial magma ocean story. There's a longstanding observation that there's about half as much argon-40 in the atmosphere of Venus that you would expect based on observations of Earth, and it's possible that this argon-40 is hiding in the basal magma ocean right now. Okay, so the conclusion is that Venus is my favorite planet, and it should be your favorite planet too. I think in the next 10 years, it should be one of the highest priorities for planetary exploration because it's the terrestrial exoplanet in our backyard, and it's it's a window into Earth's past, and if we don't stop climate change, potentially Earth's far future. We can do really amazing things with the spacecraft data that we have now, but we desperately need new missions to assess habitability. So I hope in this talk, I've given you a flavor of all the really cool tools you can bring to bear on Venus. And I hope I've raised way more questions than I've answered, and sort of helped convince you that there's things we can do in the next 10 years that would transform our understanding of Venus and therefore transform our understanding of how planets are put together and how they evolve over time. So thank you all so much.
Thank you. Round of applause. That was delightful. And we have questions in the chat and questions during the Q&A. So if folks have questions, feel free to post them there. You can also raise your hand and I can call on you. So there's some questions flowing by in the chat. I'm gonna address those first before they go away. So Misha Zoltov asked, can the slow rotation of Venus be related to the lack of magnetic field?
I either answer that question in the talk or I get it in the questions. The short answer is no. Venus is a slow rotator compared to other terrestrial planets, but it's still a fast rotator in terms of dynamo physics. There's a non-dimensional number called the Rossby number, which indicates that the Coriolis force should be very important to fluid flow in Venus. And so it's rotating fast enough that if it were convecting, you would expect a dynamo.
All right, Mark Robinson asks, he says, heat flow is a little less than Earth. Is that 5%, 10%, or 50%?
We don't know. We need more detailed studies to figure that out. The basal magma ocean models that I presented, if we found a basal magma ocean, that would tell you at the 50% level that it's been cooling that much slower over than Earth. The flexural studies, I would say, they're saying that it's like Earth-like or slightly below, but I would say tens of percent uncertainty right now based on the analyses of the local features themselves and also how you extrapolate those local inferences to the globe.
Great, and Dan Shim asked, oh, where'd it go? It's moving around here in the chat. Do we have any constraints on the bulk composition of Venus compared with Earth?
Yeah, we have one constraint, which is the bulk density. We know the mass of Venus, we know the radius of Venus, and the bulk density is similar to Earth, so people pretend it's the same as Earth. I don't know. It could be. I mean, it's probably pretty similar to Earth, but yeah, you could invoke vastly different abundances of various like minor elements that act on mantle and crustal dynamics.
Okay, and then moving over to the Q&A, Maitri Bose asks, how much CO2 is produced by large volcanoes on Earth, and how long do they need to erupt to produce the Venus-like atmosphere? 1,000 years or 100,000 years?
Yeah, so great question. I don't really have the right numbers off the top of my head. I would say to produce the amount of carbon dioxide that for the Venus-like atmosphere, you need to form about 100 kilometers of like extra crust, and you need to do it to have it happen quickly. You need to have that happen quickly. So based on the geology, we think that there hasn't been 100. So like you could do the rate that you would have to produce that CO2 that you would need to produce that CO2 over 1 billion years. That would modify the crater population in such a way that you wouldn't see the current crater population. So that vast amount of CO2 outgassing that either occurred at very early times in Venus, like in the magma ocean phase, or it occurred in this catastrophic event that happened sort of quickly all at once everywhere.
Great. Steve Simpkin asks, how spatially variable is surface temperature on Venus? Would blocking temperature be exceeded in some regions?
Yeah, so if you wanted to know the surface temperature on Earth or on asteroids or something, you have to do very complicated thermophysical models. Venus is a great planet for the lazy again, because the atmosphere is so thick that lateral temperature variations sort of average out. And so the surface temperature on Venus is just a function of elevation. It's about 1 degree per kilometer. I think it's actually a little less than that. So the highlands of Venus, like Maxwell Montes, the biggest mountains, which are about as tall as Everest on Venus, those are the coldest regions. So if you wanted to look someplace on Venus for crustal magnetism, you might target those regions. But it's also possible that those regions are young. So you want the oldest, coldest regions. I don't know what those are, so I think we should look everywhere.
Ming Ming asks, how many coronae are on Venus? Are they all caused by mantle plumes?
Yeah, there's about 500. A coronae could be produced. Again, it's just a word for like quasi-circular feature that has tectonics. So probably a lot of them were produced by mantle plume interactions. There was a great paper that came out in Nature Geoscience just a month ago that showed that if you have coronae or mantle plumes of various sizes interacting with crust of different thicknesses, you get a wide variety of final like topography and sizes, and that reproduces pretty well the variation of topography and sizes that we see on Venus. Like I said, the coronae are extremely diverse population of volcanotectonic features.
Right. Brendan Chapman asks, if Earth and Venus were initially very similar, do you find it plausible that the Earth-Moon forming impact could account for the difference in internal heat, which allows Earth's core to continue convection today?
Yeah, so it's not the internal heat so much as the mechanical mixing that the moon forming impact could provide. So for sort of, if you really do a detailed model of the chemistry of Earth's core, as you increase the pressure and temperature of the core, you expect that the metal that forms the core would have more light elements like silicon and oxygen. And that's because of the thermodynamics of how these elements partition between silicates in the mantle and metal in the core. So you expect this chemical stratification to build up if the core is undisturbed. That would create a stratification that would actually prevent the core from ever convecting. Now, if you have a moon forming impact, that'll come in, it'll hit the core, and it will mechanically stir it up. And that creates the initial homogeneous condition that you need for the dynamo to happen. So Seth Jacobson, who's a professor now at Michigan State and a frequent collaborator of people here at ASU, he published this paper about 2 years ago, arguing that a difference in impact history 4 billion years ago is the reason that Earth had a dynamo and Venus didn't. So that's why I said that the core of Venus is a probe into the very earliest moments of Venus.
Okay, 2 more questions, and then we'll be done. But they were asked a little while ago, so let's get them before we end. So Justin Cowart asks, would impact processes be sufficient to remove shallow crustal magnetization due to localized or regionalized excursions above the Curie or blocking temperatures?
I doubt it, just because so many impactors blow up in the Venus atmosphere. Like I said, there's only about 1 every million years that creates a crater. So I think the fraction of material, and I think these like sort of explosions in the atmosphere, they wouldn't heat up great depths necessarily. So I don't think so, but also I haven't looked at that in great detail. So maybe my intuition is wrong.
Okay. And then so Mark Robinson comes around, and this will be the last question. I'm sorry, somebody just asked another one. So Mark, follow up on the previous question. Volcanism seems to be significantly less than the Earth. So how is the heat escaping from the interior if the heat loss rate is only a small bit less than the Earth?
Yeah, so fundamentally, the heat is conducted from the hot mantle to the surface. So I would say it's mostly conduction, which is also the case for Earth. A lot of the heat flow is conductive heat flow. And the volcanism is probably less than Earth. Well, maybe. Again, if in the catastrophic resurfacing hypothesis, the volcanism now is a few orders of magnitude less than Earth. But if catastrophic resurfacing didn't happen, if actually these craters are like mostly filled up with volcanoes, then that's a lot of volcanic flows that have been happening in the last billion years. We know there's some active volcanism on Venus today. So I think it could be less than Earth, but I don't think we know whether it's the same order of magnitude or whether it's like a few orders of magnitude less.
All right, and then Mark just posted, this is not really a question, it's more a statement.
Yeah.
Venus had the proto-Mercury impact. How does that event fit into your story? Another seminar.
Yeah. If anyone wants me to give 10 more seminars about Venus, I'm happy to oblige.
All right, well, maybe in the spring we'll have just the Joe O'Rourke Venus
Yeah,
seminar
just the
series.
Venus series.
That
Yeah.
would simplify scheduling immensely. So thanks very much, Joe. That was awesome, and really appreciate it. And yeah, Mark says please do. And everybody who's still here, please be sure to join us next week as we kick off the fall Colloquium series. So thanks very much, and thanks, Joe, for rounding out the summer series. It's been really wonderful. Thank you.
Thank you all.